This podcast is a very rough overview of atomic structure and how the electron configuration and Bohr diagram can help us determine the type of spectra or energy we see that comes from an atom as the electrons get excited. So let's go back to step one. This is a Bohr model. And Bohr is not completely incorrect. And let's go ahead and put a Bohr model for lithium. Lithium has 3 electrons. And I want a different color. There you go. 1, 2, 3 electrons. Okay? And Bohr would tell you that those electrons, there's electrons on the first energy level and there's electrons on the second energy level. And we know from electron configuration that those first 2 electrons are 1s2 electrons. And that third electron is a 2s1 electron, correct? That's the electron configuration. And so I think that you would agree from what you've learned that the electrons on the first energy level, right here, and the second and the third, that these ones on the first energy have a lower energy compared to these, which have a higher energy, right? These were our valence electrons. They're outermost electrons. They have more energy. If you think about it, you can look at these rings on this flat Bohr model almost as little circles compared to bigger circles and bigger circles. If you swing a ball over your head, if I have the first energy level, the second energy level, the third energy level, wouldn't you agree with me that the ones on the first energy level have less energy compared to the ones on the outermost? In other words, if I was an electron, I'm running around here, these electrons, and they're running around the circle, okay? They don't have to run as fast as her. They can just go around. These are running faster to keep up, right? If you had a stick and they were all running, these outside ones would be running faster around that circle. So the electrons on the outer energy level actually have more energy than the ones on the inner energy levels. Now, keeping that in mind, we're going to compare these to a staircase. So this is the first energy level. It compares to this stair. Second energy level compares to that level of stairs. Third energy level to this level of stairs. So if I was to jump, oops, go back, do this. If I was to jump from the ground to here, or from the ground to here, or from the ground to here, the first, second, or third stair, and then I jumped off, which one would I have to gain the most energy? And then which one would I lose the most energy? If you said jumping from the ground to step 1 and then back down to the ground is less energy than jumping from the ground up 3 flights of stairs and then back down to the ground, you are correct. And that's the whole basis for the different energy levels in the atom and how they correlate to different light that you see. So to explain it best, without me going into it, I'm going to have you watch a video. Okay, and this is the electromagnetic spectrum, which you can see. We're going to go into more detail. There's radio waves, which are the size of buildings. They're very tall and long wavelengths. They don't come as often. Super high frequency like gamma rays. And what we're focusing on is visible light. And visible light's right in the middle. Okay, about the size of protozoa. That's tiny. So let's watch this video.
Okay, so when they were developing the model of the atom, there was this guy called Niels Bohr, right? He was wondering,
Ignore the birds.
why do certain elements give out certain patterns of colors when they are excited with energy, such as you get electricity, or if you heat them up with a Bunsen burner, they often give you a sort of a characteristic glow of colors. And if you look at them very carefully, you get certain stripes of colors. And he thought that these stripes of colors, since they had very specific energies, since red light has this very specific energy compared to ultraviolet light, he thought that perhaps that the electrons, when they are excited and then come back down to ground state, they must be giving up these very specifics of energy. So I've got a staircase here, and I want you to imagine that the ground that I'm standing on is called the ground state. That is, the atom is kind of sitting underneath me, and the nucleus is down there, and all the surface electrons are down there. So we're going to be looking at some of the valence electrons, the ones on the very outside. So I'm going to be a valence electron, as you watch down the staircase, that when you excite an atom, you give the outside electrons energy. And the electrons will only move if you give them just the right amount of energy. It's not really possible to get from one step to the next unless you have enough energy to get there. If you don't make it up the next step. And so you give it energy, it gets excited, it goes higher and higher energy levels, and that's what the staircase here is representing. And once you go up to these excited energy levels, you are in an excited state. But electrons don't want to be like this because this is not very stable. So what they will do is they will relax back down to ground state. But as you notice with the staircase, you can come back down to ground state in a number of different ways. You can go in one giant leap, or you could go at smaller steps. Every time you jump and land on a different step, you hit the ground with a certain amount of energy. Just the same way that an electron, when it comes down one energy level, it gives up the excess energy that it had originally obtained. And this is given off as a frequency of light. So if you jump down from a very high step to a very low step, that's a dramatic change in energy. You'll hit the ground pretty hard. If an electron goes from a very high energy level down to a very low energy level, then it will give off a very high amount of energy. This will be a very high frequency of light, something like violet or ultraviolet, or even something even further. However, if you make a smaller jump, then you will only get a small amount of energy, hence a lower frequency of light, because lower frequencies, like red, have low energy. I hope this helps, guys. Check it out. I've got an experiment coming up later on this afternoon where we actually excite a whole bunch of elements in a gas form, and you can see all the spectra, the certain frequencies of light that are emitted from each element. Alright, see you later. Bye.
And so if you notice, there's hydrogen gas, and it actually gives off different colors because those electrons are in different energy levels, as is helium, which looks completely different. And these are called emission spectra because they actually emit, and there's neon gas. Look at all the different colors that are emitted. Now I'm going to go ahead and stop this because they don't actually show as much as perhaps this picture right here. So if you look at this right here, there's continuous spectrum. And the continuous spectrum is what would happen if you look through a spectroscope. And we're going to do this next class. We're going to look through a spectroscope and you're going to see completely all the colors. There's no difference. An emission line is when atoms are excited, electrons jump up an energy level, they gain energy, they absorb heat or light, they jump up an energy level and they jump back, and when they jump back they give off light. Now if you notice, look at the emission lines and then look at the absorption lines. Do you see how they're almost negative as each other? Right? And so the absorption lines is what they look at when they look at a telescope, and they can tell what is in a star. This is a really cool thing. This periodic table actually shows different elements, and you can see the spectra. So if we look, we've got 1s2, 2s2, 2p2 for carbon. Look at that. That's what carbon looks like when you get it excited. Its electrons jump up an energy level and back, and they give off light. What about oxygen? 1s2, 2s2, 2p4. Completely different, because its electrons are jumping from different energy levels up and back. And I don't expect that you know what these are, but just know that they all have a different pattern because they all have different electron configurations. None of them has the exact same composition. Here's sodium. Look at that. There's some really light colors. See the light blue there, and there's yellow, which looks completely different than neon. Okay, and why is this all happening? These emission spectrum are happening because they're gaining different amounts of energy, jumping up different energy levels and back. So you can see here, these are different because they're all different types of elements. Okay? So there's your Roy G. Biv, going from higher frequency, actually backwards from violet to lower frequency red. And you can see in the middle of this page, there's actually different measurements. That NM is a nanometer. Nanometers are tiny, tiny, times 10 to the minus 9th measurements of color. As you can see, the upper right-hand side, white light gets split into a Roy G. Biv. Those are all the different colors. Now, we're going to watch a quick video here. Okay, and I'm going to kind of narrate, oh, where'd it go? Maybe not. Let me find it. Okay.
Electrons move around the
Here we
nucleus
go.
of an atom in concentric orbits. These orbits or shells represent different energy states that electrons can exhibit. The farther an electron is from the nucleus, the greater its potential energy.
Make sense?
While electrons typically remain in their prescribed orbital energy level, it's possible for an electron to be knocked from its lower orbit into a higher one. Thus, a bombarding free electron can collide with a bound electron, raising it to a higher orbit or energy level.
So when this happens because heat or light or some kind of energy comes from the outside of an element, the outside of an atom, and gives that electron enough energy. And if you notice, it has to jump up a whole energy level. It can't jump up half an energy level, just like you can't walk up half a step. It needs to gain enough energy to make it move from its energy level to a higher energy level. It gains energy. So step one is to gain energy.
This electron is now in a state of excitation.
It's called excited.
However, this higher orbital status is fleeting. The electron will be quickly drawn back toward the nucleus and return to its original orbit. During this transition back to its normal state, a single photon of visible light is emitted.
And so as you can see, it gives off light. So the steps are, an electron is in the ground state. As you see this atom right now, as we draw it normally, it is in the ground state. Okay? It gains energy from an outside source in the form of heat or light. You probably should be writing this down, yes? Heat or light. It gains energy. The electron jumps up an energy level. It cannot stay in the excited state, and so it jumps back. And what happens when it jumps back? It gives off energy in the form of light. Okay? We're going to watch a quick video that shows you what happens in a fluorescent light.
This repeating sequence of electron excitation followed by de-excitation is the basis for the functional capacity of a fluorescent light bulb.
Take notes.
A typical fluorescent bulb is filled with argon gas and a minuscule amount of vaporized mercury. The inner surface of the tube is coated with the powdery phosphor substance. At each end of the tube is an electrode with filaments. When heated to a high temperature, they emit or boil off electrons.
That's the source of
An
energy.
AC voltage pulse supplied by a starter pushes the electrons from one end of the tube to the other. If one of the free electrons collides with an electron of the mercury vapor, the electron is bumped from a lower to a higher energy level. The electron quickly returns to its lower energy state and in the process releases an ultraviolet photon.
It goes back to ground state.
This photon is then absorbed by the electrons of the phosphor powder lining the tube, again exciting electrons in the process. This excitation is followed in turn by de-excitation and the release of a low-frequency photon. The photons from all these reactions combine to produce the glow of white light, characteristic of fluorescent bulbs. Electrons move around the nucleus of an atom